First thing I ask you a question. Why should you attend my class? You give me an answer. Why should you as a student attend my class? Is there any need to attend my class? Give me some answer. Don't just be silent. You can always say that your class is useless, I don't want to attend. I mean, I am ready to accept that. Okay, fine. But if you attend, then why should you attend?
Sir, we want to learn about high voltage engineering, and we know that you are one of the most experienced and one of the greatest teachers. So that's why we would be privileged if you teach us about high voltage
Okay.
engineering.
Okay. This is just a straightforward answer. Any other answer? Come on, you should have something in your mind, right? When you attend a class. Yes. Okay. Yes, correct. Okay. Okay. Good. Shovankar has said something. Anybody else?
So there is too much of information in books, and we need you to show us what to learn and what not to.
Okay. Abir has raised another point. Anybody else? Anybody else? Any other reason for attending a class?
Sir, because we like to learn new things about the new subjects.
Okay. Anyway, fine. Now I have 4 or 5 opinions from your end. Now let me put forward my view. And I will say it in a slightly different way. See, first thing is, when I started my teaching career, that was 1985, long time back. You were definitely not born that time. Now, that time, there was no internet. In fact, there was no computer in our department. And there was no Google Bhagwan. That you to Google Bhagwan and Google gives you. So at that point of time, we the teachers had a good time because whatever we were teaching, going to the class and telling the students were mostly relying on that. And there are some books in the library, so they can consult those books. But things have changed dramatically. Today in 2021, you people are a completely different generation from my generation. You have so many information. Just, Abir was probably telling. You can just type a little bit in your mobile and that's it. You get it. Uh, Swati, you can send a message to whoever left that if they don't join by another 5 minutes, I will not allow.
Okay, sir.
Fine. So now, point is that now you people have that privilege or whatever you can say that you have so much information with you. And it is so readily available. In fact, there was at point of time, there was a discussion that we should not, any institute should not give, internet connection to the hostel, or even if they give, at night time it has to be switched off because students are not, learning, they are watching this, watching that and all that. But the point is now no student bothers about any institute connection. If you take a geo connection at a very affordable price, you can do anything. So you are practically full liberty. You are at liberty. So therefore, if there is a topic which you find in your curriculum or syllabus, you can go to net, get those information and read it. And I believe, personally, I believe that you are quite good student. And if there is a mathematical derivation, that derivation you can do better than me. That I am 100% sure. So therefore, if I go to the class or if I call all of you in that online class and tell all those things, then you will not come to my class or you should not come to my class. It's very clear to me. So why should you then come to my class? In my opinion, you will come to my class or you will not sleep now at 3 o'clock. It is a good time to sleep. You can log on, switch off audio, video, and sleep. But you will not do that if you understand that by attending my class, you are going to get some idea, some additional inputs, which you will not probably get from Google Bhagwan. There is a need to correlate what you are studying in the class and what is actual life, the real life. Now that correlation you cannot get from the Google. That correlation only comes from the experience and personal interaction. So therefore, as a faculty, I have seen how much the entire teaching has changed. I am now teaching for 35 years plus. So I have seen how teaching has changed. And today teaching is much more challenging, in my opinion. I cannot teach in the same way what I did in 1980s. So therefore, this course also, when I will try to take the classes, I will not just give you some equations. I will not just tell you some theories. I would like to tell you that what you are studying in this course, how is it related to real life? Then your engineering sense, the engineering acumen actually grows. This is what is my target. And how can I do it? Well, uh, I believe that there are a lot of things that could be done. There are a lot of idea views in that. It's a debatable point. But see, from experience, I can tell you a lot of personal, you know, experience that I have gained over the years. I can tell you stories, practical stories. I can give you some interactive videos like what happens in real life. And in that case, then you get a flavor of this particular course. This is so important. You should have a flavor of the course. It's not that just, you just come here, do something, get a marks and pass. Everybody will pass and get a degree. I know that. I mean, that's nothing, not a big deal. For 35 years, I have so many students all over the world. So I know that. Now I tell you a story. I start your class with a story. Yes, and that's a real story. In my life, it has happened. Nothing. It's not a second-hand story. It's a first-hand story. By the way, have you done any course on transformer design? Any answer?
Yes, sir. Yes, sir.
Yes, sir. Last
Wait,
semester only.
last semester. And how did you design the transformer, or rather, how you started your design? How was it? Taught? Just tell me. I mean, how you started when the problem was given? How you started?
Sir, we had a
And the first
reference.
step was to determine the type of core.
Okay.
And then
And
But
then
there were
we had
certain parameters were there.
Yes,
Isn't
sir.
it?
We had certain
yes, sir.
parameters,
the
and based
The
on that, we
KVA
had
rating, turns ratio, the voltage
Okay.
ratio actually.
and
KVA
Okay.
rating, voltage ratio, and cooling.
oil
Okay.
cooler air cool. This
And then some other parameters, maybe some you start with
some
some efficiency
if
or
current
maybe some,
density.
current density or flux density like
We
that.
had rise in temp, ambient temperature.
Rise in temp, right? Good, very good. So these are the ways you did the transformer design. And let me tell you, this was almost similar when I did it when I was like a student like you in 1982. So only 40 years back. So in 2002, I was in Germany I was working in ABB Corporate Research. You know ABB, right? It's one of the biggest companies in the world. So I was in ABB Corporate Research. So this was in Heidelberg, a beautiful city in Germany. I was working there. So one day I met their chief transformer designer. And I was very curious uh, that how they start designing a transformer. And remember that they don't design small transformers. They design real big transformers. And they are very expensive transformers. So I asked him that when you get an order of a real big transformer, how you start your design? Just like what I asked you, same question I asked. And the answer I got, was a shock to me. And for that, I would like to present a slide to make things very clear. Let me see where it is. Is it coming on your screen?
Yes, sir.
Okay,
Yes, sir.
good.
Yes, sir.
Now you
Yes.
see at the bottom of the slide, the shock that I got. That was his answer. Can you read it?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Do you believe it? I start the design by appointing a photographer. Do you believe this statement? I could not believe it. Then I asked that what is the matter? How a photographer comes into play? Then he said, which I have no idea at that time, that see, I am making a transformer which is a very big transformer, very expensive unit. So it has to be transported from my factory to the customer site. And how it will be transported? In all probability by road. And if it is foreign, then it will go from here to a port by road, and then from port by ship, and again from that port on the other country by road to that customer site. This is typically the route. So this photographer, what he or she will do, she will take a car, start from my factory gate and drive to the customer site using all possible routes, whatever possible route. And he or she will photograph every turn of the road, what is the angle, whether there is an overbridge, what is the height, what is the train line or whatever. After that, this fellow will come back and submit this report to us. Then our design engineer will sit with this and they will decide that this is the maximum size of the transformer which can be transported from my factory to the customer. If it is bigger than this, it just cannot be transported. It will remain in my factory. So now forget about your current density, forget about your flux density, whatever you do, this is the size. It cannot be bigger than that. I mean, believe me, I had absolutely no idea that a transformer design starts from this point. That first of all, the dimension is fixed. This is the height, this is the length, this is the width. Now, do you believe it? But this is life. And then he showed me a photograph. I will show you the photograph. Can you see the photo? Is it
Yes,
coming?
sir. Yes.
Where is the transformer here? You look at my mouse. In the center, can you see? This is the transformer. And this is the factory where it is built. You are seeing the vehicle, right? Which is transporting this?
Yes, sir.
Have you
Yes,
ever
sir.
seen such a vehicle? This is
No,
a
sir.
photo. It is a photo given to me by Siemens. You can see bottom I have written courtesy Siemens. But this is real life. This is not any imaginary Photoshop thing. This is a real life transformer. Look at that. There was a mini bus here, and it is looking absolutely a toy car compared to the transformer. Now, do you think this vehicle can a 90-degree turn? Is it possible?
No, sir.
No, sir.
Just not possible, right? And now this is a big one, right? So it has to go under the overbridge if it is there. So now you can really understand that what that chief designer told me, that if it is bigger than that, I cannot transport it. And then what happens? It remains with me. It will not reach the customer. And if your planning is wrong, then what happens? Then this happens. This is another real life photo in India. This is taken from a newspaper item. You see the bad planning? Are you seeing it? Now you tell me what to do. Either you break the bridge, you cannot do that, or your transformer will be damaged. So what has happened is an extremely bad design or bad planning, I would say. Now, when you studied your transformer design, I think this never came into picture, is it? And it was not came into picture when I was a student also. But this is exactly what I learned, and this is I learned personally from the best transformer designer of the world. So now this is actually engineering and real heavy engineering. Engineering are of different types, right? We have the electronics, this, that, but this is heavy engineering. So therefore, this is one aspect to it. So I'm closing this one. I would like to show one more thing to you. Once again, to bring your attention to what is actual life. Just wait, I like to find out the file. Yeah, here it is. See, you have all seen the switches, but mostly you have seen the low voltage switches in the laboratory and so on, right? You switch on, you switch off. What happens when a high voltage switch opens? You have no idea. So let me show you. What happened? Right. Now I would like to share a video. Just see whether the video is coming on your. Is it coming on your screen?
Yes, sir.
Good.
Yes.
Now you can see this is a substation, right? You can clearly make out it's a substation. Here is a switch. So there are three switches. Look at that. 1, 2, 3. What is that? Red phase, yellow phase, blue phase, right? It's a three-phase line. This is a high voltage switch and it's a 500 kV switch. It's a huge one, right? 500 kV. And this is called a double pole switch. Double pole means this is one, look at my mouse. This is one pole. This is the other pole. So right pole will rotate in the clockwise direction. Left pole will rotate in the anti-clockwise direction. Then this will be open. Now just the point is you will see what happens when it opens. Just have a look at it. Once more, I repeat. Have you seen any arc like this? And just can you imagine the length and the height of an arc which has been generated? But this is actually, it happens if it opens. So then you really get an idea that this is the actual heavy engineering. You have all heard that transformers, they have oil inside, and there could be a possibility of transformer fire and possible danger and all that. But you have no idea what happens when a large transformer catches fire. I'm not talking about small one. The large transformer catches fire. So if I can show you that another video, just try to let me see. Okay. So I hope I can now share it. Just see, here is a transformer. Hopefully it is coming on your screen.
Yes.
So you can see a transformer. There is a fire. But now look at it, that what happens. So I repeat again for you. Well, now I think you have an idea, right? What is the level of danger if a real transformer, big one, catches fire? But now, unless you see it, how do you know that what can happen if such a fire or such a blast happens in our electrical substation? See, there is one thing that you hear from somebody. There is something completely different if you see it. And that generates an awareness. So this course, that high voltage engineering that I am going to take, will give you some of the ideas in the high voltage engineering. There is a common confusion about power engineering and high voltage engineering. See, power engineering mostly deals with power system, and high voltage systems are part of it, I agree. But in high voltage engineering, what we do is slightly different. For that, I have to explain it slightly in a different way. If I take an electrical machine, there are three types of materials in it. Number one, the conducting material. It could be aluminum, it could be copper, like that. Second group of material are the magnetic materials. This could be steel or something else. What is the third group of material? Anybody can say?
Insulators.
Insulators.
Not insulators, right? That's a mistake. Insulation. Insulator is an equipment, but insulation is a material. So third group of material is insulation. And high voltage engineering primarily focuses on the insulation, because conductors and magnetic materials, they are different. We focus on the insulation, and then insulation has multiple categories. That's a different part. I mean, that we'll do later on. So what I'm going to do is, we'll talk about generation of high voltage. We'll talk about measurement of high voltage, and of course, why we do it. Always, every topic we discuss, there should be always a why. Otherwise, no point in teaching or no point in learning from your end. We should know why I am doing it. So therefore, I start with that one. And by the way, let me tell you that whatever I am teaching, these materials in PDF form you will get. So no point in taking notes. You will get everything. So in this class, we should have more of a discussion rather than taking notes. Notes will be, I mean, it will come to you in the soft copy. So first thing is that, and I think you can see it on your screen. It is coming probably.
Yes.
Yeah, good. Now, why we are talking about high voltage generation? By the way, our generators, power generators that are in the power station, do you know what is the voltage level at which they generate the voltage or power? Let's say Faraka super thermal station. What is the voltage at the generating station? You
So in
have idea?
KBs,
Yes.
11 kV.
No, not
KBs.
11 kV, but slightly more. You know, it is 22 kV generally. In some cases, maybe 33. So it's not a very high voltage. So generation of high voltage in the laboratories, it's for a different reason. What is that? So I would like to explain it that why we need to generate these voltages in the laboratory. But before that, another aspect I have to explain, that consider that you are an equipment manufacturer. You are generating, or rather manufacturing an equipment, an AC equipment, which will be used in, say, 11 kV line. Now, this particular equipment, when you will sell it to the customer will ask you that please ensure by testing that it will be able to withstand the practical loads. And this means all sorts of over voltages and others. Now, how do you do that? Naturally, through high voltage testing of that particular equipment. And when we do the high voltage testing, we don't do it at its normal operating voltage because that is its normal operating voltage, say 11 kV. But when it will be online, connected to the high voltage line, there will be a lot of over voltages. These over voltages are of different types. The most common over voltages will be the power frequency over voltages. Now, why power frequency over voltages? This is because of the switching operation of the power system. You all know, right? You have studied in circuit theory that whenever we switch on and switch off any circuit, there is a transience. So certain over voltages are generated. Now in our power system, there will be always some switching somewhere. So some over voltages are generated. These are generally of low frequency. So what we do, we generate power frequency voltage within our lab, but not at the rated operating voltage, but at an elevated voltage. And we apply that high voltage to the equipment and we try to see whether that equipment is able to withstand or not. If it is able to withstand, means the quality of the equipment is good. If it cannot withstand, then it is a bad quality. So customer will say that, no, I will not take it. Then you can always ask me that, what will be the test voltage? Yes, as an engineer, let me stress this point. As an engineer, in your entire life, wherever you are working, doesn't matter. You have to follow the standards. In India, you know, we have Bureau of Indian Standards, and they issue the standards for all sorts of equipment. So if you are manufacturing something and you try to sell it, then customer will say that you have to prove that your equipment follows certain standards by certain testing. And this testing has to be done in third-party laboratory. Means if I am the manufacturer, I cannot do that test in my lab, even if I am a big company. I have to go to a third-party lab and do that testing. So for that, I need to generate high voltage in the lab. Similarly, there will be over voltages due to lightning, because lightning is beyond control of anybody. And these lightnings are very high voltage. But again, there are standards for that. And lightning over voltages have a typical wave shape. It is not power frequency, it is not AC, it is an aperiodic wave. So we have to generate that voltage as per the required shape and required magnitude. So we need specific testing equipment for generating those voltages. So that I will try to explain to you that how we do that. Then we have the switching impulses. That switching generates two type of over voltages. One is at the lower frequency, the other is at a higher frequency. So higher frequencies are called switching impulse. These have a different wave shape than the lightning impulse, and therefore the generation of switching impulse is slightly different from the lightning impulse. So that will also be part of your course. And finally, DC voltage. Now, these DC voltages actually are coming into picture again because now HVDC lines are very common, and there we have a lot of equipments which we use, and therefore they cannot be tested under AC voltages. They have to be tested under DC voltages, and therefore we need DC voltage generation in the lab also. And DC voltages are also required in some of the fundamental experiments, breakdown experiments and others. So primarily, these are the three types that we'll discuss from the generation side. Now, the second part of this course will be on the measurement. Now, what is the problem with the measurement? First thing, we have to understand. See, if you go to electrical machine lab of our university, what you do, you take 1 meter from the room and simply connect it to the line. Now, this is possible because the voltage that you are going to measure can be directly given as input to the voltmeter. But now tell me that I have a voltage level of say 132 kV. Can I give this voltage to a voltmeter? The answer is no. But then how do I measure it? Yes, the common way is that you have to reduce the voltage first by some proportional mechanism. There are two very common mechanisms. One is called potential transformer. The second is called potential divider. Then we measure the low voltage, and if we know the ratio of transformation, I can calculate what is the high voltage. So therefore, we can see that there are issues involved in measuring the very high voltages, which are not of the order of say 200 volt or 300 volt, but of the order of several tens and hundreds of kilovolts. And by the way, a very small question. See, when I talk about this testing of all these things, let me try to show you one thing. Let me see where I can find it. This is actually a testing lab in India, not outside. So I would like to show you. I think it is here. Yes, it is here. So if I share it now, hopefully you'll be able to see. So I hope it is coming on your screen. Is it coming? Can you see this?
Yes, sir.
Yes.
Good. Now you can see this is a testing lab in India. And you can see I was standing there. Now on the back side, you can see these two, right? These are two testing transformers. Now each transformer can generate up to 500 kV. And together they can go up to, sorry, this is 750 kV. Together they can go up to 1500 kV AC, 50 hertz. And you can see from the dimension of the people and the dimension of the transformer, you can see the huge transformers. But they are only for testing purpose. Can you imagine this transformers just for testing, right? And then we have to measure it also. Not only generation, we have to measure it. And you can see on the back side, there is a transmission line that is being tested now from this. You can see my mouse on the back side. By the way, do you have any idea which country has the highest AC voltage transmission? Highest AC voltage transmission. Which country has it?
India.
India. What is the voltage?
12 kV.
1200.
1200 kV.
Yes. China has 1100 kV. We have 1200 kV. This is a transmission line which starts from Bina, a place called Bina. And this testing was going on partly for that. Now you can imagine the importance of that these equipments which will be used in that line, they are very expensive, and the reliability of the line will depend on those equipments. So therefore, they have to be rigorously tested. And thankfully, within India, we have now the necessary testing facilities for such high voltage level. And we are going to talk about these transformers. So this one I am showing is called a testing transformer. It is not a power transformer. It is a testing transformer. So therefore, the first thing that I would like to explain to you is the difference between a testing transformer and a power transformer. This is something very significant to know, because what we are doing in the laboratory is not for power transmission. This is only for testing purposes. So now I have already shown you the photograph of testing transformer, one of the biggest. If you come to our high voltage laboratory, when the university will be open, you can see that we have a much smaller one, which can generate up to 250 kV AC, 50 hertz. Now, if we compare a power transformer and a testing transformer, there are certain points that we have to keep in mind. This is something, that's where the practicalities come. Now, power transformer, let's say I am talking about a 400 kV power transformer. Now, its voltage rating is 400 kV. But its power capacity will be very high. Its MVA rating. That's why it is called a power transformer. So that means this power transformer, their voltage rating is high, but their power rating is also very high. On the other hand, it is a testing transformer which I have shown. Now this is only testing the equipment. But when I say testing the equipment, which one it is testing? Is it testing the conductors? Is it testing the magnetic materials, or is it testing the insulation? Which one it is testing? What do you feel?
Insulating material.
Insulating material, correct. Now, insulating materials are not conductors. They are bad conductors of electricity. So therefore, the current will be very low. So testing transformer rating, for example, the two transformers that I have shown, although together they can go up to 1500 kV, but their current rating is actually very small. It is even less than 1 ampere because that current is not required there. So the big difference in the power transformer and testing transformer is that power transformer voltage rating is high, but its power rating is also very high. Testing transformer voltage ratings are in fact even higher than the power transformers, but their current rating is very low. So their power rating will be comparatively lower. This is first difference. Okay, the first and two I have talked about together. Then the third point is, a power transformer is a continuous rating equipment. You know, there are two types of equipment. We call it continuous rating and intermittent rating. Now, continuous rating means that that equipment can run continuously for 24 hours, 24 into 7, whatever you say. Whereas some equipments, they just run for a short period of time. For example, a testing transformer. When we do the testing, we switch on, and then it might be used maybe for 15, 20 minutes, 30 minutes for the testing, then switched off. So therefore, there is a big difference in this is called the type of loading. One is a continuous load type, the other one is called the intermittent load type. And the design, etc., that whole thing changes. Fourth point, what is written here is, you know that there is something called short circuit impedance of the transformer. You know that? Short
Yes, sir.
circuit impedance of the transformer? Good. What is the normally short circuit impedance of a transformer? Normal. If I ask you as a engineer, electrical engineer, that what is the normal value of short circuit impedance of a transformer? What will be your answer? See, this is the difference. That is what we call the practical knowledge, because this you have studied short circuit impedance, you have studied, you know how to calculate short circuit impedance, but you have no idea that what is the value of the short circuit impedance. Typically, short circuit impedance is about 4 to 5%, not more than that. They're definitely less than that. Now, the point is, my next question is, you know why it is given in percentage? Impedance should be in ohm. This you have to
That
tell
is
me.
per unit value. Per unit value.
What is this
Per
per
unit.
unit value? What is this? How do you
They
get
have
it?
been they have been referred to a common base. The rated impedance, I think.
Here is I don't accept I think. You have to tell me because you are in third year, second semester. Who can tell me
Yes,
that?
sir.
With the
It
line
has
in
been referred to a common voltage and current rating.
What is that common voltage and current?
The transformer voltage and rate.
Transformer rating.
Rated voltage and current.
Transformer rated voltage and current. Fine. This is I accept. But then how this percentage is coming?
To 100.
Multiplied
No.
with 100.
100.
But before that, then you should have something, point something. Say 5% mean
Yes, sir.
0.05. How are you getting that? Is
So
it
the
ohm?
yes, sir.
See,
Ohms divided by the rated value.
So
which
ohms
way?
divided by VI.
The new
That-
VI by
that-
kVA.
VI by kVA. Then what happens? Voltage cancels. Then how it is VI by kVA? VI is kVA, isn't it? You are not getting
Sir,
that.
sir, rated voltage by rated current gives us the base impedance. With respect to that, we have to express its impedance.
This is a very simple thing. Don't go into all of that. See, basically that answer was correct. That rated voltage and rated current. The thing is, if the impedance is say X ohm, your rated current is I. So I into X is the voltage drop. And then take that voltage drop as a percentage of the rated voltage. So that means Ix by V into 100. It's as simple as that. Ix is the voltage drop, and what is the percentage in terms of the rated voltage? That is called the percentage impedance. And simply Ix by V is the per unit impedance. That means Ix is what fraction of the total voltage. Now this 4 to 5% is actually we keep it because this short circuit impedance is in series with the transmission line. If it is higher, then there will be significant voltage drop from the sending end to the receiving end of the line because this impedance is in series. So in a power line, I cannot keep it very high. I have to keep it around that maximum 4 to 5%. Power transformers will be around 4%. Distribution transformers, that means our localized transformers, they have slightly higher, 8%, 10%. But testing transformers will keep it around 20%. Why? There is a reason. There is two reasons. The testing transformers, I have already told you that they test the insulation. So therefore, when I am testing, the currents are very low. So there is very little chance of a voltage drop. But if there is a failure of the equipment, that means the equipment that I'm testing, then there will be high current. Then to limit that, if I increase the short circuit impedance to 20%, then indirectly I can tell that even if it is short circuited, transformer is short circuited, the current will not be higher than 5 times the rated current. It is straight away calculation. 20% means that. So that means if it is rated current is, let's say 100 ampere, the short circuit current will not cross 500 ampere. So it's an automatic limit. And this can happen in testing. An equipment under test can fail. It will fail. I mean, over the years, we test so many equipment, there will be failure. So that's the reason a very big difference in the short circuit impedance of a power transformer and short circuit impedance of testing transformer. This again makes a lot of difference in the design of the transformer. Now, a power transformer is hardly switched on and off, very seldom. Once I switch on a power transformer, typically, if you have to switch off the transformer, means a large area will be out of power, which means that to shut down a transformer, a lot of planning is required. And this is typically done maybe once or twice a year, just for maintenance purposes. So they have very little switching on and switching off, except of course the fault condition. Whereas a testing transformer will be almost every day switched on and off. And therefore, switching transients on the internal insulation of the transformer is much higher for the testing transformers. And therefore, testing transformer, when we design and when we design the insulation of the testing transformer, we design it differently from the power transformers. So that's another difference. And finally, a very interesting aspect is called the voltage regulation. By the way, again, I will ask you, what is voltage regulation by definition?
The voltage drop between the no load voltage and the full load terminal voltage expressed as a percentage of the full
Very
load
good.
terminal voltage.
Very good. But you should not say voltage drop. Why you said voltage drop? You should say voltage change, because it is not necessary that voltage should drop. Is it possible that voltage can go up?
In case of capacitive load, sir, it may.
Correct. Not only capacitive load current flowing through inductive impedance. Then this voltage can go up. So voltage regulation by definition, when you say, please don't say voltage drop. It is the change in terminal voltage from no load to full load. It could be drop, it could be rise. And the whole thing depends on the type of current that is flowing. Now, when I'm testing an equipment, as I said, I'm testing the insulation. So what is the type of load here, capacitive or inductive?
Inductive.
Capacity.
It will be capacitive because it's an insulation. So it is a capacitive load. That means the current that will flow is a capacitive current. And the transformer has its own impedance, which is inductive. Therefore, it's a case of capacitive current flowing through an inductive impedance. Exactly the case for voltage rise instead of a voltage drop. Now, there are two things to be keep. You have to keep it in mind. See, let me give you the practical example. Say somebody has come to high voltage lab. I am testing in our lab. And as it is an 11 kV equipment, as per Indian standards, it has to be tested at 28 kV RMS. So the voltage that will be applied at the terminal of the equipment should be 28 kV RMS. Now, when I am applying the voltage, the capacitive current is flowing through the transformer impedance, and then there will be a voltage rise from no load to loaded condition. So therefore, if I put a voltmeter and if I measure the voltage before applying the voltage, and if I see now the reading is 28, and then if I connect the equipment and if I apply the same voltage, actually I am making a big mistake because of the capacitive current, there will be a voltage rise, and the voltage could be 30 kV, the terminal voltage. And that may cause a failure of that equipment under testing. But then it is not a fault of the equipment, it is my fault. It's a failure of the testing engineer. This is the first important point. And the second point is, then I should have an idea what should be the voltage regulation, and then I should apply a relatively lower voltage at the transformer end so that the terminal voltage remains 28 kV. Now, I should know this difference. Now, let me tell you one thing. In my high voltage lab, there are people who are technical staff. And they know how to use this transformer probably better than me because they are doing it every day. So how to apply the voltage, how to connect it, etc., they know it. And they also know that if I have to apply 28 kV at the transformer end, probably we have to generate 26 kV. Then the terminal voltage will be 28 kV. They also know that. But that's where their knowledge stops. And that's where the engineer's knowledge should come. That why I stop at 26 kV. I, being the testing engineer, I know why it has to be stopped at 26 kV. That makes me the in charge of the testing. Otherwise, I remain only a technical staff. I don't become a testing engineer. That is the another aspect I always try to highlight, that there is a big difference between the technical stuff and the engineer. See, you will be joining a company after your graduation, wherever you go. If it is a core engineering, there will be people who are working in that company for last 25 years. And they know that system, much, much better than you. But still you are at a higher post. Then what is the difference between them and you? The difference is they know how to do it, but they don't know why they are doing it. They don't know that what is the reason they are doing it. That's the duty of the engineer to know. And if you know that, your value is high. If you don't know that, then you are almost equal to them. So now here I am showing you the voltage regulation of a testing transformer. So here is a figure 1 testing transformer, the low voltage winding, high voltage winding. Then CL is actually the equipment under test, the capacitance of that equipment. Then what is the CSH? This is called stray capacitance between the high voltage line and earth, which you cannot avoid. It is always there. Don't ignore it. Even though it is low, it is there. So therefore, what is the equivalent circuit? This is the series short circuit impedance of the transformer, the equivalent resistance and equivalent inductance, which you all know how to do it. Then the equivalent capacitance, which is a parallel combination of CSH and CL. This is here. And then this V1 prime is the transformer end voltage referred to high voltage side. That means not referred to the low voltage side of figure 1, referred to high voltage side. Then impedance, and then V2 is the terminal voltage, which is across CL, that is the equipment. Now V1 prime and V2 is not same. Why? Because some current is flowing. And if I now draw the phasor diagram, this capacitance draws a current which is leading by 90 degree with respect to whom? With respect to V2. I repeat, the capacitance C equivalent draws a current which is leading the voltage V2 by 90 degree. Then what is V1? V1 is V2 plus whatever be the current and the voltage drop in this equivalent resistance and inductance. And so phasor diagram looks like this. This is V2. V2 means this voltage V2. Then this is I. What is I? I is the current through this capacitance. Then drop I into Req. This will be in phase with I. Then drop I into JL equivalent. This will be 90 degree leading with respect to current. So this will be from right to left, 90 degree leading, because this is inductance. So inductive voltage and current has a 90 degree phase difference. Current will be lagging. So therefore, this is V1 prime. And quite obviously, this inductive drop is in phase opposition to V2. So V1 prime will be less than V2. So that means the transformer end voltage, this V1 prime is lower, terminal voltage is higher. So that's a clear-cut case of a voltage rise. And therefore, if I calculate the voltage regulation, typically the resistance is much low compared to the reactance, that is the omega into L. So this V1 prime, instead of writing V2 plus I into R equivalent, etc., I drop R equivalent. I write only Ji into omega L. And what is the current I? Because I said current I is the current flowing through this capacitance. So it will be V2 divided by reactance of this capacitance. So what is that? V2 divided by 1 by J omega C equivalent. So you get this expression. J omega C equivalent into V2. So therefore, what is V1 prime? I substitute this I into, look at my mouse in this equation. So I get this, look at my mouse, it is this one. So then what is voltage regulation? V1 prime minus V2 by V2. But then I find that this becomes minus. So this is typically a case of negative voltage regulation. And it is always the case when a capacitive current flows through an inductive impedance. We always get a negative voltage regulation. Can you give me any other case where this negative voltage regulation appears? Any other practical example? Have you studied something?
Faraday effect, sir.
Where it is and when happens? Where it happens?
When load is very low.
Where?
Transmission.
Long transmission line.
Long transmission line. See, your answer should be to the point. Transmission lines can be two types, short transmission line, long transmission line. It is for long transmission line when the load is low or it is unloaded. Both is possible. But then why it is negative? Where from the capacitive current is coming?
The charging capacitances of the transmission line.
Correct. So the transmission line has a capacitance with respect to R, which I just cannot avoid. So this capacitance draws a charging current, and that becomes the capacitive current. And the transmission line has its own impedance. So therefore, a capacitive current flows through an inductive impedance. So there is a negative voltage regulation for such cases, and that is called Ferranti effect, because Ferranti first found this effect long time back. Anyway, now coming to the definition of per unit impedance, I told you that current into the equivalent impedance divided by the voltage. That is per unit impedance. And Z equivalent, if we neglect the R equivalent, it is simply omega into L. And current, here you can see my mouse. This is current, so you put it here. What you find is omega square L equivalent, C equivalent. Look at the voltage regulation expression. So that means short circuit impedance and voltage regulation has some sort of relationship. What is that? They are almost equal in magnitude. So therefore, if a testing transformer, which has a per unit impedance, say of 0.2, so then what will be the relationship between V2 and V1 prime, where V2 is the terminal voltage, V1 prime is the transformer end voltage. You can see, we can put it in this expression here. See, voltage regulation is this, V1 prime minus V2 by V2, and this is equal to minus ZY. That is from here, these two expressions, voltage regulation and per unit impedance. You can see it is minus Z. So V1 prime is nothing but 1 minus Z into V2. So V2 is V1 prime divided by 1 minus 0.2, or it is 0.2, 1.25 V1 prime. So that's what I was trying to tell you, that this V2 is the terminal voltage. So if I want to apply 28 kV at the terminal of the equipment under test, I cannot have a transformer voltage which is 28 kV. It should be much lower, because there is a voltage regulation involved in it. So there is a problem. Just read the problem statement, then I will explain. A 500 volt by 250 kV testing transformer is required to test a cable. This is an important point, to test a cable. The test voltage level is 150 kV. That means 150 kV has to be applied to the cable. And the short circuit impedance of the transformer is 16%. That is, Z is 0.16. Calculate the voltage to be applied to the primary, that means the low voltage side, to conduct the test. Because remember, it is always easy to measure the voltage at the primary, because primary voltage is 500. Now, to test a cable, this has an interesting statement, because cable draws mostly the capacitive current. So it is indirectly saying that you should take it as a negative voltage regulation. So in our case, V2 is 150 kV. That should be the terminal voltage. Z is 16%, that means 0.16. So the transformer voltage referred to high voltage is 150 into 1 minus Z. So it comes to 126 kV. This is the primary voltage referred to secondary, that means on the high voltage side. So now when I refer to primary, that is to the low voltage side, simply by turns ratio, it comes to 52 volts. So if I apply 252 volts to the primary, I get 150 kV in the secondary. So this is something that we should know when we perform such things in our lab. Next point is slightly different. That is what is called the potential distribution along transformer winding. This I will take in my next class. But now tell me, you can ask me, we can spend a few minutes on if you have any questions on today's discussion. Any student has any question? You can feel free to ask questions. No questions? Anyway, from next class onward, I would expect that you will ask some questions. Then I will understand that you are engaging yourselves to the subject. Otherwise, it will feel like you are not engaging yourselves in the subject. And when you engage, then you really get, you know, you can enjoy the subject. And whatever I'm trying to tell you, you can see that I am trying to correlate with whatever we do in real life. And then you will also get that feeling that this is exactly what is done in real life. Anyway, if there is no questions, uh, then I would like to stop today. And next class, as I said already, I have told you, I think you have seen that there is a 2 days that I have earmarked for your class. Only one small thing will be there because I am in several committees in the national level and others. So if something comes up, I will inform you beforehand that there will be a change. Then we'll mutually fix up another alternative date. Okay, thank you and take care. Best wishes.
Thank you, sir.
Thank you, sir. Thank you.